Welcome to Chemistry 111. For those of us who were at the class today, may notice this is a little different from what we experienced in class. That is because there were some issues with the recording software, and I am re-recording this for everyone's benefit. Let's jump straight in, and that most of our information will be up on Google Classroom. Will be up on Google Classroom, and from here I will post all information you'll need. I will post various things like the syllabus. I will post all the lecture notes are available here, and all the assignments, including their due dates, are up on here. Most of the assignments will be submitted through Achieve, which I'll show you in a minute. But for now, we'll just take a look at this. So let's first look at the syllabus. So what we have here is what you can expect. Depending on which group you're in, I'm going to skip straight down to the important thing, which is instruction. Depending on which group you're in, you will be either coming to the Monday or Wednesday or Friday class for that week, and we are alternating. So those who are showing up on Monday and Friday on this first week will be showing up on Wednesday next week, then back to Monday and Friday. There's only 2 days where this is not the case: the week of Labor Day and the week of fall break. The week of fall break. So every other class will be alternating. So make sure you know which group you're in. I will invite you to Google Meeting, whatever, or live stream. Try to get you on. But just note that if you miss it, I will be posting these on YouTube at a later date. Hopefully that same day. The book is all going to be online, and it's going to be Achieve. We're going to talk about this. Though I ask you to try to engage on the Google Meeting as best you can, just note that this is for your benefit. I'm trying to help you guys as best you can. So you can watch these later, but it's harder to interact when you watch them later, all things considered. We've got a homework score. It'll be 35% homework assignments, which are all on Achieve, 10% for each of I think 3 or 4 exams. Let's see. 4 exams. This is Achieve. You can get here by going to achieve.macmillanlearning.com/start. I asked you to already create an account for here, so we'll go ahead and sign in. while the cards to register for here may not be in at the bookstore yet. It should be in within a week, but hopefully you can access this course, Bethel University 111, Chemistry 111, Fall 20, Evans, uh, early, and get like say a free week or so. It seems I already have 5 enrolled at this time. I'm going to go ahead and click on here. So this is going to be your ebook as well as your where all your assignments are going to be located at. As we'll see. Right now, nothing's due. We'll see in the next week or so, at the end of the week, these guys are going to be due. August 22nd for all these. So we have reading, which is 5 points. Really easy to achieve. You click in here, you read the section, 5 points. We have now there is more sections in this in the ebook, but I am choosing to only require you to do those readings. So if I click chapter 1, we can go through all this: the properties of matter, classification of matter, properties of matter, matter and energy, scientific methods, international system of units, significant digits, and all this. But at this time, I'm only asking you to read 1.6 and 1.7 because I consider those to be a little bit more difficult. So, going back. So, reading, not very hard. The learning curve is a little bit trickier. So, the learning curve is worth 25 points. You have to achieve a certain target score in order to get the 25 points, but you are not penalized for guessing. This is to teach you, and it will give me your accuracy, but it's to teach you kind of how to do those, some of these harder topics. So for example, this question is valued 15 points. Add these numbers together, correct significant digits. Knowing what I know about significant digits, I know this is the answer. I get 15 points. It explains why. And you can challenge the question if you think it's wrong. If you do this, it's also worth 15 points. If I get it wrong, oh no, the answer is not correct. I can try again for a full point. So I can try again to get 5 points. But if not, it also tells you, okay, you can read more in this section of the book. Get help in other ways. So you don't have to just keep guessing. But so that was only worth 5 points. So you keep going on like this until you achieve the 100 points. You can always come back to this later. So I have 20 points done. If I want to come back to this later, it will be waiting for me. You can keep doing that. That'll give you easy 25 points. You are not penalized for getting ones wrong, but it goes faster if you don't just guess. So those are typically due sometime around the expected time we're going to finish a chapter, maybe a week afterwards. The homework assignment, which is a little bit more in depth, is due before the test. So these guys right here, homework for chapter 1, is a little bit more lengthy, but but you can do it at any time. There's say 22 questions in this one. I tried to keep them somewhat short. There's going to be a wide variety of easy and medium difficulty, hopefully not too hard, but they will help you as you go. So, like, look, some of them are multiple choice, some of them are fill in the blank. So let's look at this. Say, label these guys as homogeneous, heterogeneous. What type of mixture? That might be homogeneous mixture. It's pretty uniform throughout. This is two things combined together. It's a compound. There is heterogeneous. Well, this is a pure element, just all glued up. Check answer. It's like, oh, I'll give you the point. Okay. If I do that, I would get 100% points on that problem. So, which is heterogeneous? Oil and water. So I'll do this. I'll try this. You can always get a hint. Heterogeneous mixtures have non-uniform colors. Check answer. So, and you get it wrong, it'll give you feedback. When oil and water are mixed, two distinct layers form. When salt is mixed with water, it completely dissolves. Only one of these mixtures is heterogeneous. So it usually gives you some feedback. So you'll attempt. You can try. There's ways to try again, and then you'll. But so you can try again. And it can show you what you did. Go from what you did to, oh no, fix this. And notice, like, this one, 5% off. So keep in mind, you do not have to do all these problems, but if you want all 50 points, you would have to do all 50 problems. So if you do 21 out of 22, you would have something like 47 and a half points. So keep in mind, if you leave a couple empty, it's not the end of the world. And you can always come back and do them later for some partial credit. But I'll have to fix that so you're not penalized too much for guessing. And you're not penalized too much for being late, but try to get it done on time to get the maximum amount of points. But that is what you can expect from the homework. And I will be doing my best to try to update your scores in Google Classroom. So this chapter is just the quick run through the basics because, hey, we need to be able to have the same starting background. If this is a little awkward, it's because I'm trying to teach a new book, just giving a try, where this is called Adams First Approach. So rather than focus so heavily on the math, we're going to save the math to the very last little bit. So we are not going to do, we will maybe introduce the moles, chapter 3 or so, but we will not get to stoichiometry and a whole lot of difficult conversions and titrations till the end of the year. We will focus on how do we look at atoms and electrons and protons and neutrons and how they all fit together. So this is going to be working at atoms first. So I've tried to modify my slides, but I'll be honest, and I didn't put I didn't put as much effort as I probably should have. So I'll see what I can do and change things as we go through the semester to maybe make this better aligned with the book. But we've all been busy. So, okay. So why should we study? Oh, geez. Why should we study chemistry? Oh. Okay. Well, just trying to get everything hooked up. So we want to understand how things work. We should be able to go through life saying, oh, nothing should be a black box. If we end up in a Mad Max style scenario here where we're driving through the wastelands of America looking for guzzling or mother's milk, we want to know we want to be the ones who survive because we know how a car works. We want to be able to get through knowing that we can understand, well, hydrocarbons burn. We do this. I'm currently working on putting a wall of COVID information
right there on the chemistry board over there, finding a bunch of good articles explaining pretty much every subject you could want. Like, how do we know disinfectants work? Which masks are best? Can we trust this mask versus this mask? Which drugs work? How do these drugs actually work? Not just magic, COVID die, money machine go burr. We have to go, well, it attacks this protein and stops it in its track. What does this drug do? This drug doesn't actually stop the COVID. It actually prevents the overactive immune system you have from killing you after it's defeated the COVID. And so there's a lot of interesting stuff out there that's really, if you take all your information from Facebook, will give you a bad time about what's going on. So there's lots of stuff out there that we can learn about, like solar panels, LED lights. If you're in biological field, you've probably heard of the term MRI, magnetic resonance imaging. What is that? How does that work? Besides being big magnets, this was actually developed from chemistry, an analytical technique that used to find the radioisotopes of carbon and hydrogen and help us say, oh, this is the compound we indeed have. Was further modified to be able to like look at the individual slices of a human body without slicing the human body up into ribbons. So all this stuff comes back down to chemistry. I also want to gain some critical thinking skills. It's not so much that you come out of here and you know everything there is to know about chemistry, because unless you're in chemistry or biochemistry or some sort of heavily chemistry field, biology, you might still need to know some of the stuff. But if you're not in biology or physics, you may not need this after here. So what good is it for coming through this class? Well, hopefully you'll have critical thinking skills. The idea is you want to, it's not so much what you know, but how you learn what you don't know, how you attack that. In fact, if you are to graduate with an undergraduate degree and go on to a graduate school, it's more about specialization and learning how to learn stuff, learning how to attack problems you do not currently know how to fight. So how can you study things? How can you get, it's not so much I know this right off the top of my head, but how do I find out that answer? How do I read papers scientifically and find out what do they really say, not just what the headlines say? Like, scientists say they can cure cancer by smelling farts. Well, that's just what the ignorant news media will read, one headline, one little part of the paper, and that's the big pull away they have. But what do they actually mean? And so that's hopefully what we'll be able to get. You can read something and actually learn, what does this say? And hopefully we can appreciate, even just appreciate the work that comes into everyday life. Cell phones, all the metals that go into your cell phone, all the, how do we get plastic? How do we degrade plastic? How do we save the environment from being over plasticked? How do we build any pharmaceuticals? Even the nylon and polyester that we're wearing right now, all chemicals that came from this, came from chemistry in general, synthesis. Every dye, even when you're making your sourdough, that's chemistry, chemistry of baking. You're understanding right there how the yeast is reacting and making the bread to rise as it's producing CO2. That what makes the sourdough sour and all that fun stuff. All that comes from chemistry, and hopefully we can appreciate that by taking these classes. And ideally, we want you to be a better citizen, able to interact more intelligently in a scientific discussion. So if you're going home for Thanksgiving, you're going to be arguing with old Uncle Bob or whatever about this and that, hopefully you'll be able to speak intelligently and not just yell across the turkey. So we'll start with talking about matter. We'll just give the base background of all the little terminology that we have. That First, what is matter? Matter is just anything that has mass and occupies space. It's a really general definition, but everything here has matter. The only way it doesn't have matter is if we can't weigh it and it doesn't take up any room. So that leaves like pure energy generally doesn't have any weight, doesn't really occupy any space. And pure vacuum doesn't really occupy any weight or space, but everything else is typically matter. And I know this is kind of a circular definition, but mass is just the measure of the quantity of matter. So how much does the matter, how much heft does it have? I mean, solids, liquids, gases, plasma, they all matter. Even if we can't see it, it's matter. Air has weight, which is part of the reason we can feel air pressure. But air is there. But, okay, so got mass, we got matter. We can break this down into different things now. So pure substance. A pure substance is a definition that says we have matter that is the same composition throughout and cannot be separated into components by physical means. So if I have a bucket of sand, if I sift the sand, I'm not going to break it into like anything other than just sand. If you took some sand from the beach, might be a little bit different. You might have some shells in there. You might have, I don't know, trash that someone threw in there. There's lots of different things. That would not be a pure substance. But pure substance could be an element, could be a compound, could be something else, but it cannot be separated by physical means. And we'll get to what I mean when physical means in a minute. We're going to use these terms a lot: elements, compounds, and mixtures. So you got to make sure we're on the same page when we discuss them. An element is the simplest type of a pure substance. So if we look at an element, it's uniform in its properties, and it cannot be reduced to a simpler substance by chemical means. We cannot break down this into anything other than what it has by chemistry. So if I take a block of iron, it should be iron throughout. And we chop it up, we do whatever it is, it cannot change from iron. It's still iron. You take a piece of coal, try to break it up, you break it into smaller bits, it's still carbon. Chemistry can convert it into something else, but we cannot change carbon from carbon. So an element is just one type of a pure substance. A compound would be a mixture of two or more elements that are chemically bound together. So like if I put carbon and oxygen together, we become CO2. And now we have a mixture of the element carbon and a mixture of the element oxygen chemically bound together. I cannot just take a knife and chop this into carbon and oxygen again, but there are chemical means to separate them. And so oftentimes we're going to talk about mixtures. Mixtures are just going to be two or more elements or compounds that are put in the same area without being chemically bound. So each one will be chemically unique. So if I talk a mixture, air is the penultimate mixture. The air is the mixture that we deal with every second of every day. And if we suddenly aren't dealing with it, you're dead. Air is mostly nitrogen, a good deal of oxygen. We have a little bit of CO2, a little bit of water, a little bit of argon, and a bunch of trace gases. But all of these guys are separate. They're bouncing around together, mixed up, but they're all chemically unique. If they start interacting, it'd be a little bit more of a problem. But so as long as oxygen is in there, we're breathing, we are alive. So now we can break down mixtures into two types, homogeneous and heterogeneous. And as we describe these guys, sometimes when we have these terms, they come from either Greek or Latin, or so if you can kind of get the terminology down, we can better understand this. So that homo is, we're talking about same. Hetero, we're talking about different. So homo means same, hetero means different. So when we talk about a homogeneous mixture, it's the same throughout. We talk about like air. For the most part, air in this room is the same throughout. That, which is good, because then you won't walk around, run into a pocket of nitrogen with no oxygen, choke out and die, because oxygen is uniformly spread throughout this entire room. So there's lots of things. If you mix in sugar to your Kool-Aid, or you stir it up real well, it's uniformly mixed. Your Kool-Aid's going to taste the same all the way through. You don't stir in the sugar, you get a big clump of sugar at the bottom, you have a heterogeneous mixture or heterogeneous mixture. You're looking at, as you drink the Kool-Aid, it's going to go from watery to sweet as you get down to the bottom where all the sugar is. So depending on the mixing, you could have heterogeneous and homogeneous. Finally, one last quick definition before we move to the next slide is atoms. Atoms are the infinitesimal small building blocks of matter that can be made of any type of element, but individual atoms can only be one type. So when I look at an element is made up of atoms, but each atom could be a different element. So I could have an element, a little atom of iron, another atom of iron, and then suddenly an atom of carbon. And each atom is a different element that I cannot break these guys into anything simpler than iron. I cannot break this carbon anything simpler than carbon. But so a compound is made up of atoms of an element combined together. CO2, for example. Just a quick picture. CO2, as we'll learn, is carbon to oxygen. So we atom of carbon, an atom of oxygen, another atom of oxygen. We have two atoms of oxygen bound to one atom of carbon to make the compound carbon dioxide. So, but we need to know that terminology so as we continue going forward, we can talk about this intelligently and all mean the same thing. So, quick flow chart. We don't need to learn this. We don't need to memorize this, but just a quick way. So, matter. Everything is matter. Can it be physically separated by physical means? Yes. Then it must be a mixture. Is it uniform throughout? Then it's a homogeneous mixture. No, it's heterogeneous. If it can't be physically separated, it's a pure substance. Can it be decomposed chemically? If we can break it down chemically, it's a compound, meaning it's made of one or more, two or more elements. If I can't, it must be an element itself. And then further, we could break it down into like conductivity, whether it's a metal or a non-metal, but we're not going to focus on that so much. But this is a flow chart I stole that's really nice. Okay, let's check the time. So we got another 10 minutes. Okay. So talk about properties of matter. We have physical and chemical properties. We could talk about extensive and intensive and physical and chemical changes. So first, physical properties. The physical property is a descriptive property that we can observe without changing the compound. So you can observe its color without changing its color. You can observe its odor. We can weigh its density. We can melt it. But melting goes from solid to liquid. How is that not changing its properties? Well, if you melt it, you can usually refreeze it back into the solid again, and it still retains its properties. If I melt iron into like liquid iron, it's still iron. It hasn't changed. I can put it back. I can measure the boiling point of something. The same way, I can boil it, but then I can condense it back. I can measure the hardness of a substance. Its conductance. Does it conduct electricity? All these are examples of physical properties that can be observed without changing. The chemical properties are essentially properties that talk about how it reacts with something else. Like, does it burn? Because burning is an interaction of oxygen and the substance. So carbon, is it flammable? Yes, because if you've ever grilled with charcoal, it's flammable. Acidity, how well does it donate a proton or accept a proton, which is a hydrogen atom? How well is that relates to how it will change. Citric acid is a very acidic compound. Acetic acid, which is vinegar, very acidic. Citric acid, like oranges, lemon juice. You should all know that. You should all be able to recognize that in your everyday life. Oxidation potential. How well does it give up or lose electrons? All these things we will talk about later. We're not going to focus on them right this second. So, but oxidation potential, like how well that relates to flammability. But for example, iron will rust. It's rusting because it's oxidizing in the presence of oxygen. Now, extensive and intensive properties, I will not really focus on these super much, but there's still a property we can look at. Extensive properties depend on the quantity, like mass. If I have one marker has such and such mass. If I have 5 markers, suddenly we have a lot more mass. If I have one piece of charcoal, we have a little mass. If I have a dozen pieces of charcoal, I have a lot of mass. So those are extensive properties. Intensive ones will not matter. Like if I take one piece of charcoal, the density of charcoal is the same. If I take 20 pieces of charcoal, if they're uniform, the density of charcoal is the same because the density is mass over volume, which will not change as we scale up. And an often question that gets asked is on tests and on homework is identify a physical versus chemical change. Physical change is a change in physical appearance, but not its composition. There's no changes in its actual chemical or physical properties. So if I melt this or I break this into smaller bits, as long as the atom composition are the same, it's a physical change. Chemical change is the substance is transformed into another substance, such as rusting or any type of combustion. Example that I always give that's kind of really tricky. So if you say, cut the grass. Cut the grass starts with starts with a physical change where you're cleaving the grass from the other parts of grass. It's not till the grass begins to wither and rot that it undergoes a chemical change after the fact. as you eat a candy bar, you are starting with a physical change of you're breaking it into smaller, more digestible fragments, drawn by a chemical change where you're physically starting to digest it. But the digestion is the chemical change. The mastication, which is your chewing, is more of a physical change. But during the chemical change, a reactant, or oftentimes multiple reactants, will undergo a rearrangement and the chemical bonds become what we call the product. Okay. We will finish with this slide. So we will do this slide and we'll call that a day. And next on Wednesday, when you guys Skype in or the Google meeting in, we will talk about, we'll start to get to a little bit of math. So matter and energy. Chemistry is usually the study of the interaction of matter and energy. So remember, mass is the measure of matter. So real quick thing, mass is actually different from weight. Weight is the effect of gravity on mass, because most measurements are taken on Earth. Mass and weight are synonymous because we take that 9.8 meters per second squared acceleration into account. But if you were to go into outer space and weigh yourself, your weight would be very little. Your mass would still be the same. You would still take up the same amount. You'd still have the same amount of matter. You just wouldn't weigh nearly as much because the weight scale is measuring the effect of gravity on that. Now, energy is the capacity to do work. We'll talk about the law of conservation of energy, that essentially one thing we learned is energy cannot be created or destroyed. It can only be transferred. So if I do some physical work, the energy had to come from somewhere. If I'm pushing a block, where's the energy coming from? The energy is coming from me, which is coming from the combustion of food particles that we're going through the various biological cycles that's producing energy that gets us here. And so, but it had to come from somewhere. Where did that come from? That came from the digestive process that ate that energy and turned it into the fats and proteins and lipids that my body is going to use. And as we talk about energy, we'll talk about work. Work is the force applied over distance, which is a mechanical type of energy. But we could have lots of different energies: heat, chemical, mechanical, electrical, nuclear, sound, electromagnetic. We will talk mostly about chemical energy, but we'll talk a little about heat, a little bit about kinetic and potential, and a little bit about electromagnetic this semester. Next semester, we'll talk about some nuclear energy and a little bit of electrical energy. But for the most part, we'll focus on heat, chemical, and electromagnetic. So that's where we're going to stop for today. Okay. And I thank you for your... What the? Thank you for